السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. So we will continue the first part of session 7, which is about randomness, and then inshallah we will move to the second part, which is I think more interesting. The remaining part here is talking about appending arrays. What do we mean by that? If we have an array and we want to add an element to it, then we use the numpy method append. We call it with the array that we want to append the value to and the value that we want to append. So this will, as we saw before in other methods, will create or will return a new array with the value appended to the given array. We'll see, of course, example. And the value has to be of the same type as the other elements in the array. We can also append two arrays. Of course, appending will happen to the end of the array. So appending two arrays, we will append array 2 at the end of array 1, and this also will create a new array. Like merging them, but it's not. It's just appending all the elements from array 2 at the end of array 1, and we'll create again a new array. And again, the elements have to be of the same type. So let's go through a quick demo on this. If I have two arrays, first and second, and then I append 6 to the first. So what is the first array now? From 0 to 3. And how about the second? From 10 to 16. When I append 6 to the first, what will happen? We'll get 6 appended to from 0 to 3, right? Now, when I print first, what will I get? 0 to 3, okay, without 6 because it returns a new one, okay? Now, when I append both first and second, I will get an array of length that is the length of the first plus the length of the second. When I get first now, the original one, and the second is the original one. Okay, if I want to get the new one, then I have to assign it. Here is another example. So this is creating an empty array. If you remember last time when we did the simulation of rolling one die, okay. So this is that's the method that implements one experiment of this. I think we have to probably run it here first. Then we can call it from here. Now this will append the result of that experiment to this array. Okay. So now after we running this cell, what will we get? Yes, if you remember, good that you still remember that the outcome is not from 1 to 6. It was -1, 0, 1, depending on the number. What happens here? One round is not. Yeah. Okay. So it's something that we didn't. Die faces. Okay. I think this is what we. Oops. Still, what's one round? One round.
It's at the top.
The top? No. What's going on here? Name one round is not defined. The function one round. Okay, sorry. Okay. So there's a function one round here. Yes. Okay. I'll do that. Now, I think it will work. Yes, so we get the first, we get one element. If we call it again, we get another outcome, right? That would be appended just because we assign it to the same array again. Okay, and that's another one. Okay, so that's another example of appending to arrays. Any questions about appending to arrays? Okay, now, sorry. Now we'll talk about iteration, and of course you are familiar with iteration. Here we will focus on the for statement. So for is a keyword that begins a control statement when we run a block of code multiple times. Okay? So we control the number of times that a block of code will execute, and the purpose is to do a computation for every element in an array. That's usually the usage of a for statement. So let's see a demo to see how for is written in Python. Okay, so we use, of course, the reserved word for. Then this is a variable, okay, and we use again the reserved word in, and then this is a list or an array of items. Okay, so what is the semantic here? So that variable will take the value of each element in that array or list. Okay, so we say for pit in, and this is an array. Now pit will first be assigned to cat, and then the block will be executed, then assigned to dog, then assigned to rabbit. Okay, and notice that there is a colon here. And whatever we want to execute as the body of the for loop will be indented after the for statement. So what do we expect as an outcome of this cell? 3 statements. Okay, so I love my cat, I love my dog, I love my rabbit. Okay, and if you look at the next cell, this is exactly what happens when we call the for loop. So this is just a simulation of what happens when we call this specific for loop. Pet will get assigned to the first item, then the second item, then the third item, and for each, the body of the loop will be executed. Okay, so this is a standard for loop, but the syntax here is a bit different than the other maybe languages that you are used to. We use the reserved keyword in, and then the list that we want to go through. Now, if I want to do something for, let's say, 5 times, how can I do that using the for loop? Then I have to use an array that has the values from 1 to 5, and the usual way to do that is using a range function. Okay, so that if we look at that, what will happen? So game outcomes is an empty array here. Then we have a loop, and the loop is over an array from what? From 0 to 4. Okay, so usually this number is 1 more the last index. Okay, which is the number of times if we use it that way. So here we will run our experiment how many times? 5 times. From 0 to 4, that's 5 times. That's usually the number that we have here if we use it that way. Okay, so by running this cell, we will get 5 outcomes, 1 from each experiment. And if you remember last time, the outcomes were -1, 0, or 1, depending on the random value of the die.
We wanted the previous one to print just the 2 first.
Sorry, say it again.
Yeah.
Here.
Just to print the 2 first.
2 first?
The cat and dog.
Then the array has to be cat and dog only. Or you can have an if statement that will exclude rabbit. You have to do it yourself. So whatever, you cannot say I want the from elements number 3 to elements number 5 from the array. No, you have to. So what will happen is that every iteration, this variable will be assigned to the next item. You cannot say I want these numbers. You have to create another array, or you do it by conditionally within the body of the loop. Okay. How about this one? Looks similar to this one, right? What's the difference? We'll just run it 50,000 times. Okay, that's running the same experiment, but instead of 5 here, 5 times, it will run 50,000 times. Okay, so we can do it and this is, if we want to make sure what's the length of the array, then we call len. This is 50,000 now. We can add, of course, the results to a table. If we want to look at the distribution, then it's better to use a table. So we can add it to a table as a column, and then now the table has just one column, which is the net gain here. And then, if we are interested to see the distribution of the outcomes of running the experiments multiple times, then we can use, of course, bar chart. Okay, you have to group first, and then we use bar chart. What do you expect here? What are the different outcomes here? -1, 0, 1, right? If we visualize the distribution, what would you expect? Remember the experiment, the one experiment is that we will roll a die. If it's 1, 2, the value will be, if it's either 1 or 2, it will return 1, right? If it's 3 or 4, 0. If it's 5 or 6, it will be -1. So what do you expect the distribution will be?
It will be the values of the table and how many times it empties.
Yes, how many times, but how about the percentages? What do you expect?
The -1 is the highest.
-1 is highest? Why is that?
Because it results one time.
Ah, you are looking at this. But this is the top 10 rows only.
Okay.
We have 50,000. Okay, so you cannot just look at the numbers here. This is just the top 10 rows, right? But now we want to look at the distribution over the 50,000. That's why we are actually using 50,000. Okay, what do you expect? 3 bars, I understand. Okay, are they equal or not?
We don't know.
We don't know. They should be close to equal or not?
It depends.
Why is that?
Because we have only 3 values.
Okay.
So the randomness will be equal.
Yes, because they are equally probable, right? One has the probability of what? 1/3, right? Because it has 2 cases out of 6, and also 0 and also 1, right? So -1 and 0 and 1 all are equally probable. So we expect that we have a uniform distribution actually. Uniform distribution means that all the possible values are equally probable, right? So we'd expect something like this.
Always if the sample size is small.
Ah, okay, that's a good question. So we did it over 50,000, right? As you increase, and we will discuss that further, inshallah, I think during this week or early next week. As you increase the sample size, you would expect that these numbers will get much closer. Okay, and as you saw here, the first 10 you might not get similar percentages like this, of course. So as we increase the sample size, we will get eventually to the uniform distribution. And even with 50,000, you see, this one is a bit higher than this one, right? It can happen, of course, because this is just random. But as we increase, if you have time at home, if you want to increase 50,000 to 500,000, okay, you can do it and see how the distribution will be. It will be much closer to equal here. Okay. Any questions? Here's another experiment. The experiment here is about tossing a coin 100 times and counting the number of heads in the 100 times. So we have a coin. The coin has how many outcomes? 2, head and tail. We toss it not just once, we toss it 100 times. Okay? And then we count the number of heads. If we do that, what do you expect as a number of heads? It should be around 50, right? It should be around 50. Let's see. So we'll do this simulation to see if that's true or false. Okay, I hope that you know the answer, of course, but we'll do it by simulation. Okay, to do it through a simulation, we have to repeat that experiment multiple times. Okay, so this is an example of how we can do a simulation in general. Okay, so let's first see what are the outcomes that we have. So the coin has two outcomes, head and tail. So we define an array of all the possible outcomes. Then this is the experiment. Okay, we want to get the sum of heads. Okay, sum of heads of 100 samples. So we'll have to take 100 samples. If you remember the choice method, remember last time? The choice method will randomly sample from an array of possible values. Okay, so this is the array, and this is the number of times we want to sample. And then we, to get the sum of the values here that are head, we compare this array. This will give us an array, right? Will give us 100 values, 100 samples. We compare it with head. This comparison will give us what?
Number of heads.
No, without the sum.
Only the heads.
No,
Array.
it will be an array of true false. Okay, if it's head, it will be true. If not, it will be false. And when we sum, if you remember last time, when we sum, it will give us actually the number of truths. Okay, so if we do that once, we get 46. This is just one experiment. But actually, we want to do it more than once, because as you saw, one, we got 46, but that's not what we expect in general. Okay, so to do that, we have to run this multiple times and draw the distribution as we did in the previous example. So that the general procedure here is 3 steps. The first one is to simulate one experiment, which we have just done, but here we will put it into a function. So that's exactly what we did here, but now it is inside a function called number of heads. Yes?
What's the purpose? We will do many experiments?
Yes, so the purpose is that I want to see the distribution of number of heads if I do this experiment. Okay, or I want to see the probability, but I don't want to calculate it. Okay, one way to get the probability, as we will see later inshallah today, is by counting. So we'll do this experiment multiple times, and we'll see how many times it will give us 50, and how many times it will give us 49, and so on. Okay, so we'll draw the histogram at the end. So the first step is to simulate one experiment. The second step is to determine how many times you want to run this experiment. Okay, of course, as we run the experiment multiple times, we should get better estimates of the probabilities. Right? Right? What is the downside of this? Time. Time. Of course, that will take more time. So here we decided that we want to run this 10,000 times. Now the third step is to simulate the whole thing. So easily we will have a for loop, and we call the running of one experiment inside that loop. So we define an empty array, and then this loop will call the experiment 10,000 times. Why is that? Look at the code. Yeah, so repetitions is 10,000. Yeah, so A range will give us an array from 0 to 9999, right? Which means 10,000 times, and for each we will call the experiment. And we'll append the outcome of the experiment to the outcomes array. So at the end of this, the outcomes array will be an array of what? Of the values from each experiment. Okay, which is the number of heads in each experiment. Okay, so it's important to understand the process here. We first define what is an experiment, which is I want to get the number of heads if I toss the coin 100 times. So that's the experiment. Okay, now I will repeat it 10,000 times. So I will eventually get 10,000 numbers, which is this array. Okay, so you see sometimes we get 49, 46, 53, and so on. Now I want to see the distribution, then I will use a histogram. To do a histogram, we need a table. So we add the outcomes as a column in the table. Now the table has one column, and then draw the histogram with bins, because I'm expecting something around 50, so the bins here is somewhere between 30 and 70.
Each experiment
Will give us one number.
we toss the coin 100 times?
Yes, so that's one experiment. And we repeat that 10,000 times. Okay, so what do you expect for the histogram? Do you expect equal, uniform like what we get earlier? You don't expect uniform.
Yes.
So uniform means that it is equally probable to get one head and two heads and three heads and four heads and five heads until 100. Is that the case here? No, we said that it's more probable to get 50, right? Because if you remember the probability here, the coin is fair, so it's 50% chance to get head and 50% chance to get tail if you run that 100 times. So most probably you will get 50 if you do that multiple times. Okay, so you would expect that the highest probability will be around 50, and then below and above it will be less probable. So you will get something like this. Okay, so the highest probability, although here it's not exactly the highest probability, that's just because this is, of course, maybe the sample size is not yet enough, although it's 10,000, but if you run it more, you will get it. And it looks like what? The normal distribution. Okay, so the mean is about 50, and then the probability goes down when we move away from 50. Okay, so that's a way of looking at probabilities by simulation. Yes, you have a question.
It's always uniform distribution.
Is that uniform distribution?
I mean, not the probability that counts as the distribution. I mean, each, for example, in head is 50 and this one is 50.
Okay, good question. So we assume here a fair coin, but sometimes the experiment might have different probabilities for different outcomes. Yes, it might be, of course, yes. Okay, if you don't have more questions, then we'll move on. Good. So the remaining part of this is optional. It's about an advanced where statement. It's straightforward. I will leave that to you. So it's just one slide and there is the demo on it. So you will do it yourself, and we move on to the second part of the session, which is about what we call Monty Hall problem and probability. Any questions before we switch? Okay, good. Anyone familiar with Monty Hall problem? Okay, so that will be even more fun than I expect, I think. Okay, the Monty Hall problem. So what is this? You know it now. Okay, how many of you know it? Just one? Okay, so, huh?
We talk about it in
Okay, so keep silent as much as you can. Okay, of course you can join the discussion. So what is this? This is a simulation of, this is the game. Actually, it's a TV program. I think it was around 1960. So what is that? It's like a contest, and the winner of the contest will get a prize at the end. Okay? Now we are at that stage. Someone won the contest, and now he or she should get a prize. The process of getting the prize is as follows. We have 3 doors. Okay? Behind one of these 3 doors, there is the prize, which is a car. Okay, so the prize here is a car, but you don't know, of course, which door the car is behind. It's one of these 3 doors, and the other 2 doors have goats behind them. Okay, so one only has a car, and two has each of the other 2 has a goat. Okay, now you should choose which door you select first. Now let's say that you selected the second one first. Okay, so you selected the second one first. Now when you select the second one, the presenter of the program, who is called Monty, will not open that door, but he will open one of the other two doors. Okay? He will open one of the other two doors that has a goat, because he knows in advance where the car is. Okay? So of course he will not open the door that has the car. It might not happen actually. So he will open one of these two doors that he knows that there is a goat behind it. So for example, I chose door number 2, then Monty will open one of the first or the third door that has a goat. Is that guaranteed that there is a door that has a goat from the other two doors?
Yeah.
Of course, it is guaranteed because we have two goats. Okay, so at least one of the two remaining doors has a goat. Okay, fine. The game didn't end yet. So now you selected first door number 2, and Monty revealed one of the other two doors to be a goat. Okay, so now the final step is for you whether you will stick to the same door you chose in the beginning. Okay, and in that case, of course, Monty will open door number 2 for you, and we'll see if it has a car or not. Or you say, I want to switch to the other door. I want to open the other door, not the first door. So you have the choice. And based on that choice, you will get the car or the goat. I don't know actually if you will get the goat, but anyway, you will not get the car at least. Now the question is, what should you do? Should you stick to your first choice, or you should switch to the second door? Can you please discuss that between each other and tell me? Based on what? No, that's the question. Based on what you need to decide whether you would stick to your first choice or switch. Think about it. If there's no basis, then tell me. Randomly, I can choose randomly. Tell me. Discuss, please. Okay? Think together. But of course, if you know the answer, don't share it. You got the answer, خلاص. Okay. If you got the answer, then think about it. Why? Take a minute and think about it. Don't tell the answer if you know it. Any ideas? Yes.
I'll stick to number 2 because.
You will stick to the first choice.
Yeah.
So whatever you choose first, you will stick to it.
Yeah.
Why?
Because the remaining probability that one of the doors has a goat is the same for both doors.
So your answer is basically doesn't matter.
Yeah.
It doesn't matter, right? So you can choose the number 2 or number 1 in this case.
Yeah.
Doesn't matter. Okay, so that's your answer. Other answers? Except the ones who know the answer? Huh? And all of you agree that doesn't matter? We should take 1 or 2? So what do we mean to say it doesn't matter?
Means the probability is the same.
It means that the probability is the same, right?
Yeah.
So we can choose randomly 1 or 2, it doesn't matter. Any other answers? Let me ask you, what is the probability that the car will be behind door number 2? Half?
It's 1/3 before.
It's 1/3.
Yeah.
It's 1/3. What do you mean by before? It will be the same. What do you mean?
After, so it's 1/3.
Because two, you didn't know anything about 2, right? So 2 didn't change.
Yeah, I mean it's third and this one is third, so
Okay. So you're saying that the probability here is third, and the probability here is third, but you know that the total probabilities is 1, right? Where is the third?
there.
No, but now.
Here you know, so
Okay, but when you choose now, the total probability should be 1, right?
yeah.
So where is the remaining third? What happened to the remaining third?
So I don't know.
Oh, yeah. You cannot say just the probability of number 2 is 1/3 now, and the probability of number 1 is 1/3, because the total should be 1.
The other third is the third door. Yeah.
But you know that it's a goat. You will not choose the number 3, right? I don't think anyone will choose number 3 now.
So that's
Unless you like to have a nice animal like
So
that.
it's now 50-50, that's what we are saying here.
So it's 50-50.
Yeah.
Okay.
Number two and
So all of you agree that it's 50-50. Okay. It might not be clear. So let's see. Okay. How can we check that? By simulation. Right? We can do simulation. We can play the game, simulate it, and do it multiple times. Isn't that what we did earlier today? Right? To check the probabilities, we can do simulations. So we want to simulate this game. So one experiment will be running this game once, and to get a good estimate of the probability, then we have to run it multiple times. Okay? Is that a good plan? Good plan? Okay. Now let's go and do a simulation. Okay, Monty Hall. So how can we do the simulation? As we said earlier, it's a procedure, right? We have to define what is one experiment. So the one experiment here is the game. Okay, is running the game once. How do we run the game? Now, without looking at the code. How do you run the game?
The first step, take the array.
The steps, right, of the game. What are the steps of the game?
Make the array for the third element.
Okay, so we have 3 outcomes, right? We have 3 things. We have car, we have first goat, and we have second goat, right? And then the contestant or the winner will choose one of them randomly, right? So the winner will choose one of these 3. Then, after choosing that one, what will happen?
One round, the method of one round, we will
Huh?
change the conditions of it. If it is door number 1, so set to this one.
So Monty will have to open one of the 2 other doors based on what he knows about what is behind the door that you chose or the winner chose, right? So there will be the winner choice, yeah, Mariam. There will be the winner choice. There will be the door that Monty will open, and there will be the remaining door, right? So these 3 things will be the outcomes of the experiment of playing the game. What did you choose? Or the winner, and what Monty will open, and what is remaining. Type. What is the outcome? So this is the process of the experiment. What is the outcome of that experiment? The values of these 3 things, right? Type. What do we want to do by repeating that experiment? What do you want to see? We want to compare what? What are the probabilities that we want to compare?
Door number 1, door number
If we stick
It's not door number 1, door number 2 by numbers. It's, yes,
the remaining doors.
the remaining door versus
So
the chosen door. Versus the door that you chose first. Right? Right? Or it's one of these 2 options, right? The one, either you stick to what you chose first, which means that you will get whatever is behind, or you switch to the other door, so you will get whatever is behind the remaining door. Okay? Good. So we will define an array of the 3 things that we are choosing from, and this is just a helping function. So what does this function do? Look at it.
It will give us the door that have the goats, the second goat.
No.
No, the remaining goat.
Yeah.
I mean, if
Okay, so look at the function by itself. What does the function do? What does it take and what does it return?
Takes the first goat.
Can you be with us, please?
Yes.
Okay, so what does the function do here?
I put the first goat and the second goat,
Mhm.
and then we'll return the other value.
Okay, so given one goat, it will return the other goat. Okay, so if I give it the first goat, it will return the second goat. If I give it the second goat, it will return the first goat. Okay, so this is a helping function that we will use in the experiment. So if we call it by the first goat, what should we get? Second. If we call it with something other than the two goats, nothing. We'll get nothing. Okay, now this is the function for the game. This is the function for the game. So we said that the first thing is to choose one of the three values, right? So we'll call choice over those. What are those? The three values, the first goat, second goat, and car. So that means that simulate the choice of the winner. That winner chose one door, and behind that door, it's either a car or one of the two goats. So now this is the contestant choice. Based on the contestant choice, we will choose what Monty will reveal and what will be behind the remaining door. Okay, so what is this?
If the contestant shows
Yes, if the choice was first goat
or second goat,
or the second goat, then the choice of Monty of course now there is only one remaining goat, right? So we'll have to get the other goat. That's why we had the function other goat. We'll get the other goat and that will be Monty choice. And the remaining door in this case will be the car. There's no other choice. Else, which means
if the contestant's choice is the car,
was the car. Yes, so if the choice was the car, then Monty choice can randomly choose one of the goats and the remaining door will have the other goat. Okay? Clear? And eventually we'll return these three values. What the contestant chose, then what Monty will open, and the remaining door. Okay, once we define this, we can call it, this is one experiment, and here is one experiment, which means that the winner chose the first goat, and the remaining door has the car. Okay, we can call it another time, third time. Okay, every time it will give you one possibility. Now, to do that, to collect statistics, then we have to run it multiple times. So we'll put the outcomes in a table so that we can easily visualize it. And so this is just the labels of the table. And we'll run it here 3,000 times. Okay, we will run Monty Hall, which is this function, 3,000 times. Okay, let's say that we run it 3,000 times, we get this table. Of course, every time we will append the outcome to the same table, and we'll get this table. Now, what should we look at among this table? What is this table? What is each row here? One trial. That's one trial. Okay, so each row is one trial. So in the first trial, our guess was the car, and the remaining has the first goat. Okay, and the second similar, and so on. So what should we do now? What should we look at?
to the output of the
So what do we mean to have this row? It means that if the winner stick to his guess, he will get the car. If he switch it, he will get a goat. And the same with every row. Okay, so what should we look at now?
The guess and the remaining.
The guess and the remaining. Very good. The guess and the remaining. What exactly in the guess and the remaining?
What the contestant could choose.
Yes, so how many times probably in the guess, how many times I will get car? And in the remaining, how many times I will get a car? How does it look like from what you saw here, what you see here?
The remaining is better.
The remaining it seems better?
No,
Should we conclude that? No. Why not?
because we only see 10.
Yeah, that's 10 rows. That's 10 rows. It might be confusing. Okay, it might not be a good guess. Okay, so it seems like cars here is a bit more, right? Actually, no. How many times we have car here?
Same.
5. How many cars we have here? 5. Okay, so it seems like the same, right? From 10 rows, but we don't know if that will be the case in the remaining table, in the remaining rows. What should we do now? Bar chart. Okay, so before bar chart, maybe we should do counting. Just count. How do we count?
Number 0.
How can we count here? How do we do counting? Group. Okay, so we should group. Okay, let's do grouping on remaining. So that it will give us each value. Car how many times? First boat how many times? Okay, so let's do that. Just before the bar chart, we'll get the counts. What do you expect? We don't know. Yeah, roughly what do you expect? So we ran this experiment 3,000 times. Huh?
1,500.
Huh?
Goats have more.
More chance. So how many cars you will get out of 3,000? 1/3. 1/3. So around 1,000? 1,000? Huh? For the car, 1,000? How about the first goat? 1,000, 1,000, right? So we would expect the same among the three. Okay, so let me do that first on the guess, not the remaining. Let's do that on the guess first. Okay, so for the guess, what do you expect?
1,500.
1,500. For what? For car? So guess here, you expect that you will get 1,500, which is 50%. For the car in the guess column. It should be the same, right? Same among the three categories. So if that's the case, then we should get something around 1,000. Okay, let's see. But it's around 1,000, right? Of course, if we run it more than 3,000, probably we'll get closer. But it seems like equal here. Okay, so for the guess column, the probability that we will get the car is around 1/3. Right? Did you say 1/3? Okay, so it's around 1/3. That's for the guess, the choice, right? The guess. Okay, now let's look at the remaining. Do you expect the same? Same. Right? Yeah, but around 1,000 for each. Right? Okay. Huh? Same. Okay, everyone is saying the same? Okay, let's see. That's the count that we get here. So what does that mean? So that's around 2,000, right? Right? And that's around 500, which means that the probability to get the car from the remaining door is 2/3. That's 2,000 out of 3,000, right? It's 2/3, which is, you said, higher, right? Someone said higher here. Higher than what? Higher than the goat, I understand. but higher than the guess, which means we should change. Which means that we should change. Is it guaranteed that if we change, we get the car? No, but it is higher chance to get the car if you switch. Okay? Okay, you don't believe in these numbers, right? Seems like. If we don't believe in these numbers, what should we do? Do it again? Or better, do it? Better? Do it with more times. Run it more times. Okay? So let's, instead of 30,000, let's do it 30,000? 30,000. Okay, it will take time, I think. So you see here the star, that means that it is running until it runs. Why did we get these numbers? And it seems like the probability for the remaining door is 2/3. And the probability for the guess is, for the choice, is 1/3, which means that the probability is double if you just say, no, I don't want to stick to my choice, I want to move to the other choice. So what happened? It's done? Okay, let's see again let's see the bar chart directly. Okay. That's almost 20,000, which means it's clear it's 2/3, right? If you don't believe and you have time, at home, add one more zero and run it and have the fun. Okay, now it seems like, yes, the probability is double. Okay, so the probability is double. Now getting back to the slides. So that means that if you play this game, what should you do? Select anyone in the beginning and then switch blindly, right? Then switch, and the chance to get the car is double the first choice. Why? That's the question. Why? Do you know why? You know the answer, right? Oh, okay. So you thought that it's 50-50. Okay, that's even more fun. Why? Why we got this answer? So no one actually expected that it will be different. Now, it's not by, how come it's by chance? The probability is almost 2/3. It's not by chance, of course. Running it as an experiment, of course, by chance, but as you run it multiple times, the counts will give you an estimate of the probability. So now we want to know, why is that? You will not leave until we know why is that.
They take the cost to the other.
No, they didn't change anything. No, they didn't change anything. The car is still there whenever it was, and the two nice goats are there. So there is no tricks here. Yes? دايما نظرية المؤامرة. Okay, no, it's not. Why? Why not? Why did we get this? By the way, it's not straightforward to many people. Okay, I read about that. There is a discussion. Of course, there was a discussion among mathematicians about this. So it's not very straightforward, but there is an intuition, of course, and I hope that you will understand it. So here is my simple explanation. Okay, even if you didn't understand it, try again. Okay, and read more about it. But of course, we kind of proved it experimentally, right? So it is a fact that it is different. The probability is different. Here's my explanation. If I chose 2, then of course, because it's one among the 3 doors, that the chance that the car is behind that door is 1/3, right? Right? So it's. I think this is clear. This is simple. It is 1/3 for whatever it chose first. Now, what is the probability that the car is in one of the other 2 doors? No. Okay, let me say the question again. We said that it is 1/3 the probability that the car will be behind that door, right? Now, what is the probability that the car is behind the other 2 doors?
The probability of the
It is the probability that the car is behind this plus the probability that the car is behind this, which is 2/3. Okay? Now, why now the probability goes only to door 1? Because door 3, we are now sure that the goat is not there. Okay, so the remaining door actually moves here. It's not fixed. The remaining door might be this one or this one. So the probability that the car will be in one of these two is 2/3. Is the mass probability that was allocated to the other two doors. Because now one of them is clearly 0 since we opened it to be a goat. So the remaining probability all will go to the other one. And if you noticed, I don't know if you noticed or not, the remaining door is not fixed. It's not always one of the others. It is based on where the car is. Okay? So the mass, the remaining mass of the probability will go to the other door, which is 2/3. Yes?
I didn't get to what you said, it's not always fixed.
Okay, so it's not always fixed among the experiments. Yeah, sometimes the remaining door might be the first one. Sometimes the remaining door might be the third one. Sometimes the remaining door will be the second one. It's based on where the car is. Okay, if it's fixed, it would have been 1/3. But it is changing based on what you chose in the beginning. Okay, so it doesn't stay as random as it was in the beginning. It is deterministic once you chose the first door, and it changes. It changes across experiments, I mean. Okay, if you played the game multiple times, the remaining door will not be a specific numbered door. It won't be always number 2 or always number 1. It depends on what you choose. If you're still not convinced, you are a normal person, okay, because it's not very straightforward. Read about it again. I provide a link, and also it is explained in the textbook.
But Dr. actually, it's not a reason to say because we did one, now the probability is 2/3 because we compare this one with this one. And if we compare the chosen door and the remaining door,
Yes.
so it would be the same, 1/3, 1/3.
But you saw in the experiment it is not the same, huh?
But now the explanation when you say it is 1/3 and 1/3.
No, I didn't say 1/3. I said 1/3 versus 2/3. I said 2/3. Because the probability that it will be in the remaining door is the probability that will be in one of the two other doors. It's not just one specific door. That's why it is 2/3. It's not 1/3. Okay, so we're done with this, and this is quickly another way to see the answer. Okay, another way to explain the answer. Okay, what is this? If the contestant pick the car, then Monty will throw away a goat, and the remaining door will be a goat, right? You agree with me on that?
Yes.
Type. What if the contestant pick the first goat? Then the second goat will be here, and the car will be in the remaining. What if the contestant picked the second goat? The first will go here, and car will be here. So we actually have 3 possibilities. Only 3 possibilities. 3 different possibilities. Okay? And among the 3 different possibilities, how many times the car will be in the choice, in the first choice? Once. And how many times the car will be in the remaining choice, remaining door? Twice. Okay? And that shows you that the probability is 2/3 here and 1/3 here. Okay? Any questions? Okay, thank you, and we'll continue next time, inshallah.